Alright, so we understand density conceptually now with sinking and floating objects. Now let's look at it more mathematically. Alright, I want you to write down this formula right here. It's super importante, right? This is the formula for density, which is mass over volume, okay? That's important, write that down. And the units for density could either be grams over milliliters or grams equals centimeters cubed, right? Because volume, right, if you have a box, right, it is kind of like length times width times height, right? And that's like multiplied, and it gives you an exponent of 3, right? For this example coming up, I also can say that density is equal to kilograms per liter. So that this unit works as well, okay? Everything is just multiplied by 1,000 for grams and milliliters, okay? So, density is a derived unit coming from mass and volume. And density is an intensive property, meaning that is independent of the amount. So what that means is that if I have like a rock, right? I have like a tiny rock, right? That tiny rock's density is going to be the same if it was like a gigantic rock, all right? That value of density never changes for that specific rock. Okay, it's unique to that rock independent of its size and its amount. So we can use a digital balance to measure mass, and you can calculate the volume of a box by measuring the length, width, and height of the box. So here's an example right here. Once again, it's like what I drew earlier. Volume equals length times width times height, giving you centimeters cubed. And the type of calculations is easy to do for objects that are shaped like boxes. However, not all objects come in regular shapes. How can we measure the density of something like a rock, right? A rock is kind of like weirdly formed, and we can't really have it defined length times width times height with straight lines. So how are we going to figure that out when I'm measuring my volume? Let's look at it over here. And I'm going to give you a little story, all right? Story time. In a well-known problem, Archimedes was given the task of determining whether King Hero's goldsmith was replacing his gold with another cheaper alloy. Archimedes wanted to determine the density of the metal, but he had to figure out a way to do it without melting the metal down and smashing it into a cube or sphere where the volume could be calculated more easily when compared with the weight. Baffled, Archimedes took a bath, and as he got in, he observed the rise of the water in the bathtub. Therefore, he thought that maybe he could calculate the volume of the metal by using the displacement of water. Okay, displacement of water. So, allegedly, upon this discovery, Archimedes went running through the streets in the nude, shouting, "Eureka, Eureka!" In Greek, I found it. Alright, so Archimedes was this dude, right, really well known for math back in the good old Greek days. And displacement of water just shows you how much water changes, right, in height. So we've all probably experienced this when you were in your bathtub. As you sat in, right, the water kind of rose up as your weight sank into the bottom. Hopefully it didn't overflow and got over your bathroom. So, what does that mean? This is useful for measuring volume when you have weird shaped objects. And we're going to use this principle to find the density of a rock. Okay, and I'm going to use a math simulation, little virtual simulation to figure out what is the mass, right, and also what is the volume of it in, we're going to actually find it in liters in the simulation. We're going to find it in liters, and then instead of grams, it's going to be kilograms, okay? So, we'll fill this out by doing a simulation. So, check this out. Alright, Mr. Blockman right here is 10 kilograms for mass. So I'm going to write that over here. So mass is equal to 10.00 kilograms. Whoops. Okay, and then the volume right here, I'm going to say that the initial volume, I'm going to call it VI, is 100 liters. Okay, so now check out what's going to happen when I get this rock or this brick. I'm going to put it in the water like that. And look, the water rose up to 105.00 liters. So let me write that down. Okay, so VF is equal to the 105.00 liters. Okay, so now how do I find the volume of my rock? Okay, what's the volume of my rock? What I actually do is that I just find the difference, or I subtract the final volume minus the initial volume, right? Just the change is going to tell me the volume of the rock, how much the water changed. So all I do is, right, I do 105 to 0, okay, minus 100 is going to give me 5 liters, okay? And I would put decimals and the 00s there, but I just running out of space. So when I do the VI, let me erase some of this. Okay, let me erase some of that. So how I found that was, okay, VF minus VI gives me the V rock, which was 5.00 liters. And this is what I was looking for, okay, for my volume. So the volume is just the displacement of the water by subtracting the final volume minus the initial volume. And then if I have these two values, I can find the density. Okay, so let's go back to our slides and input these values. Alright, here we are back at it again. Alright, let's remember that the formula for density is mass over volume. So all I'm going to do is I'm going to use this value up here, right, 10 kilograms and then 5 liters, and just divide 10.00 kilograms by 5.00 liters. And that's going to give me 2.00 kilograms per liters for my density. Okay, so pretty awesome. Oops. And yeah, so now I want you to, we're going to do some practice problems, but make sure you write these down in your Go Form list and also in your notes.